weather forecast. Peter is of German nationality, obtained master and PhD in Cologne and Hamburg at the universities there. And before joining ECMWF, he also worked for the German Aerospace Center. Also, he conducted research at NOAA and at NASA in the US and at IPSL in France. He's author and co-author of over 100 papers and book chapters, and his current duties include the management of the recently launched Scalability program, and he coordinates the Horizon 2020 project ESCAPE and co-coordinates the Center of Excellence EasyWays. Both deal with weather and climate, of course. So the title of his talk today will be Forecasting the Future Role of HPC in Weather and Climate Prediction. And I guess, Peter, that is a medium range forecast, yes?
Yes.
So.
Thanks very much for the introduction, Thomas. It's an honor for me to be here and give this presentation. I already gave a shorter presentation last year, and then Thomas obviously thought it was not too shabby, so he invited me for the keynote. But it's a big challenge to do that, and I will try to make it light so that those of you who are not familiar with weather forecasting or climate prediction will get a bit of an insight of what it takes. I'm sure you're all very familiar with your weather app that makes you decide take an umbrella or not. Fortunately, not now at the current weather conditions in Frankfurt. But what is behind is very complex, and I'm trying to present to you that it's eventually going to be an exascale problem, even though it's not quite one yet. So the European Centre is a European organization, not to be confused with the European Union. It has very similar member states, but it was founded 40 years ago with the idea to centralize in one place scientific excellence, minus myself, and HPC power. And it has been very successful since this time. So for 40 years, it has been the world-leading center in terms of medium-range weather prediction. So it's a very successful European project. So before I go on, I'd like to thank a number of people, mostly from ECMWF, but not exclusively. Peter Düben, Niels Weddy, Thiago, actually in the audience here. Björn Stevens is a professor at Max Planck in Hamburg. Mike Hawkins, ECMWF as well. Willem de Koning, Peter Messmer with NVIDIA. Thomas Schulze, CSCS, and the teams involved in projects that we actually participate in the context of HPC. Right, that works. So, a bit of history, first attempts. I've like 4 slides on a bit of history and background of NWP and weather prediction. Like the first idea is that weather needs to be predictable and is most likely predictable, stemmed from General Fitzroy, who happened to be the captain of one of Charles Darwin's voyages to South America at the time. They didn't get along very well with each other, but they both excelled in their respective disciplines. And he wrote a number of letters from which you can see these quotes are drawn to the Times, which was a good journal at the time. I particularly like this quote down here: "Those whose hats have been spoiled by umbrellas having been omitted." But basically the motivation for his attempts to measure pressure actually at the time, and from this predict weather to a certain extent, stemmed from the need to protect sailors' lives, to give storm warnings basically, and reroute ships. So later, this became more physical, more scientific, and in the end numerical. If you look at the pictures here, they're from parallel efforts in the US and Europe at the same time, Cleveland Abbey in the US and Willem Bjerknes in Europe, that basically formulated the first set of equations that are still used today in weather prediction. And they're mostly based on fluid dynamics, obviously, but of course they included simplifications because at that time the knowledge was not present to cast the equations in full form with all the prognostic variables that we are able to use today. But the person really who advanced weather prediction and who introduced the numerical concept was Louis Frere Richardson, who at that time tried actually to formulate and cast the equations, the analytic equations, into a numerical framework to solve them. And his first attempts to do that were not very good. The outcome was actually wrong. It was later understood why, but nonetheless the methodology was correct, and it was really the first time this was ever done. So a very important result and kickoff of numerical weather prediction, and this is where the term numerical comes from. Then later, computers became involved. At the time of Lewis Farr Richardson, it was actually a manual process. So if you think of today's weather forecast being run on thousands of cores, at that time it would have been thousands of scientists doing the calculations manually and communicating by shouting, actually, of course. Later, when computers were involved, that changed, and you all know John von Neumann's project at the time, investing into electronic computing. And one of the sub-projects was actually on weather forecasting, and that sub-project was headed by Jules Charney at the time, also produced great inputs to the formulation and further refinement of the equations that we use today. One of the first calculations, and I think the publication was published in 1950, was performed on ENIAC. That was a computer that sat at the time in Maryland. It was quite a beast, as you can see from the power consumption, the weight, and the way it was constructed. The first forecasts were done in a very simplified way. It was basically just covering the US. It had a number of grid points, like 16 times 19, with not equal spacing over the US, but of the order of 400 to 700 kilometer resolution, therefore. And unfortunately, the single 24-hour forecast took 24 hours, okay? But it was a demonstration at the time. So later, some students put that on a Nokia, and later means 2006, which is many, many mobile phone generations ago, and the same forecast took only 1 second. So this tells you something about the evolution of computing at the time. So another very important milestone is the introduction of uncertainty, the concept of uncertainty and probabilities. Obviously, for any kind of prediction that is not exact, where you have model errors, which you have to initialize somewhere and the initial conditions are imperfect, you need to quantify uncertainty. Okay, this is shown in this graph up here, that we need to initialize our models, but it's not a point with exact knowledge of the current 3D state of the global atmosphere. But there's uncertainty illustrated here by this circle, and then you have model error. Your model isn't perfect as well, obviously. And so what you do is you launch a whole bunch of forecasts with slightly different initial conditions and some sort of formulation of model error inside the model itself. And what you get is a certain area that is spanned by this area here. This is more narrow than the climatology, so because you want to beat climatology, you want to have a more precise forecast than what's always the average forecast for Frankfurt tomorrow, for example. So you have to narrow the space that you cover in terms of predictions. But you do this by 50 or 100 individual forecasts called ensemble forecasts. And what you see here is a map of that, how we do this today. So you basically get 50 different scenarios of likely weather evolutions in like 4 days or 10 days or something like that. Okay? So this is what we do today. The concept was born by Ed Lawrence. I think most of you know this kind of little butterfly graph, and he's probably can be rightly termed the founder of chaos theory, and he introduced this into meteorology at the time. And we still do that today at all scales. So in terms of predicting only a single state of the atmosphere, we predict a probability distribution of states. And that's very important, for example, for extremes prediction, where you look, if you have a probability distribution, you look at the tails of these distributions, okay, for extremes. Right. So much for the history. Today's scale. The good thing about weather prediction is that you can verify it, and we do it every day. We use about 40 million observations per day in our analysis system that creates the initial conditions. And this is about the number of observations we have available to verify every forecast every day. So this, in terms of an application, is quite unique that we can do that. And what you see in this graph is a time series of the evolution of skill. So this is a certain skill measure, it doesn't matter which one, and the higher the better. And you have here time series in different colors for different kind of weather parameters, like surface pressure, Geopotential is like an incarnation of large-scale dynamics. Lower level temperature, 2 meter temperature, 10 meter wind, and cloud cover. So most of these are actually weather parameters we can all relate to, so they're very important to us. So getting them right is important. And you see they all go up. So there's a steady improvement in predictive skill due to many reasons, and we get to that. But they don't go up in the same way because they depend on different things in the model, basically. Depending on when you change resolution or when you improve a physics scheme or one thing or another, you get then improvements in one of these parameters. But it's not very straightforward to do that all the time, everywhere, 24/7. So that's one important thing, but the main message is we can verify our predictions every day, and we do that. The other thing is, and being in Europe, it's an area where Europe is actually worth leading. If you take one of these measures, and again you do a time series of skill, you see that the European models, the blue and the red, are actually leading the pack compared to other models. And I think that's quite outstanding, actually. And that proves also that the concept of centralizing excellence in HPC in one place pays off. Okay, so second message for this view graph. Now, in the future, we expect improvements come from a number of areas. The obvious one is model resolution, of course. Another one is model complexity. We have to, of course, understand that becomes increasingly important if we go to longer range, that the Earth is not just an atmosphere, but that the atmosphere is affected by the ocean as well, land surface, sea ice, maybe the higher atmosphere even, and so forth. So we have to add model complexity to enhance skill. And largely, I mentioned the ensemble component already. And ideally, we use the same type of models to run long integrations, so many time steps. So in terms of predictive skill, resolution buys you accuracy, ensemble prediction or investment in ensemble prediction and ensemble members buys you reliability, so predicting the probability distribution well, and complexity buys you range, because many of these processes in oceans are slower than in the atmosphere, and so if you couple with the ocean, you get a better grip on the longer scales. In terms of cost, obviously this is just copies of models, so this is linear in HPC. This is a bit worse than linear, because it's not just a linear superposition of added prognostic variables, for example, so this is probably more costly growth than linear. And this is about cubic, okay? Time step and 2 dimensions in the horizontal. So this needs to be traded off against each other, depending on what you actually want to do with your forecast model. Now we have to discuss one concept a little, so I need to spend a minute on this slide. Since we're limited by resolution, and I mentioned this cost factor of cubic, so you need to think about whether you want to invest in resolution or not, because the cost growth is cubic. So obviously you do not resolve all scales. So some scales like small clouds, convection, some radiation effects, some land surface effects like city, the urban cover of land on the large scale is actually not resolved and not accurately represented in models. So if you take a set of equations that I just mentioned, we don't have to go through the equations, but the black parts are actually resolved. So we would actually describe them in our model very accurately, as long as we have enough resolution for them. But the red guys, they come from these parameterizations, and they're very important. So if our parameterizations are very crude, they will affect the accuracy of these predictions very strongly. So ideally, you have a lot of resolution so that you have as little parameterization as possible. But again, that comes for a cost, okay? So the only real solution is, if you want to get rid of these red terms, is to crank up your resolution, okay? So if you look at this, one big factor in the middle here is convection. So the deep convective clouds that you see in the tropics, for example, storm clouds that we'll see in a couple of days probably here, this kind of thing is parameterized right now, and it's a large source of error in all models. And it is even though these systems are quite fast developing in the tropics, for example, and then they rain out, so life cycles of half a day or something, they affect large-scale circulation. And we believe that both in weather and climate, the link between the tropics and the higher latitudes, so mid-latitude weather, depends a lot on how accurately we can represent convection. So ideally, we don't need a convection parameterization. Ideally, we resolve it. But that means that we need scales of about 1 kilometer resolution. Okay? Right now, we're about 10 kilometers. And then you could play this game further down. The further you go down, you will lose other parameterizations and have a more accurate model, but of course there's limitations with computing. But I want to make this one point that right now what we formulate as our leading key science case is that we would like to have the global capability at 1 kilometer in our Earth system model with about a calculation rate of 1 to 5 years per day. Okay, at ECMWF, it's a bit less, it's 240 days per day, so which is like 3/4 of a year, but that's about the figure, okay? And if you calculate that, how many grid points you have and so forth, layers, variables, ensemble members, that's an exascale problem, okay? So that's a very important science case, and we can formulate it, and we all agree on it. Okay, some scaling graphs. We just did them recently. These are based on the ECMWF model. Most of them are actually single precision, except this curve here. So just let's focus on the other ones, but that. So what you see here is this forecast days per day figure I mentioned before, and I said we were aiming at 1 to 5 years or something. At the center, as I said, it's about 240 days per day, which translates to completing a 10-day forecast in 1 hour. And we do this twice a day and with an ensemble. Okay, so this is kind of our threshold. So if we look at these different experiments, today we're running in a single forecast 9 kilometer, that's this curve. And in ensemble prediction is actually twice that, so it's not even on the graph. In like 5 years, we would like to run this as an ensemble. And you'd say like, okay, well, what's quite safe here? We can run that thing easily on 120 nodes or something, but times 50 in an ensemble, that's already bigger than a single cluster that we have. And if you go to higher resolution, and I mentioned how important resolution for us is, so if you project this to 5 kilometers or 2.5 kilometers or 1 kilometer, our global key science case, you see we're way off. Now this is 1,000 nodes on our Cray, times 36 in terms of cores, so this is about 35,000 cores, times factor of 15 short, if everything scales well, times 50 ensemble members. Far away from it. So, are more flops going to make us happy? In a certain way, yes, because all these curves are going up to a certain degree, even though the model is clearly not efficient enough to benefit from this up to where we need it. Okay? So in a certain way, the answer is yes. In another way, it's not the case, because if you look at the history of our computing at ECMWF, and here's the time series in terms of sustained teraflops, and it's a log scale with a linear fit here, so it's an exponential growth, if you wish. You see the sustained over peak performance has gone down to like 5%. And this is something that all Earth system models basically suffer from. It's very inefficient. Okay? So this is something that we have to work on. So are more flops going to make us happy? To a certain degree, but not really, because 5% is just not going to get us there. So what's wrong? For this, we have to look at our problem, the problem that we integrate with every time step. So it's a bit of a complicated graph again, but we'll take our time. So if you take one of our equations here, you have a prognostic equation for wind in this case, and you have two terms that relate to the resolved part. So these were the black terms in the equations before. And then you have two other terms that relate to parameterization, so that those were the red terms, or coupling. And coupling means in this case, coupling the atmosphere model with a wave model or an ocean model. So you have different contributions every time step from all of that, because as your dynamics motions in the atmosphere evolve, you get heating by lifting or sinking air, and then you have, let's say, condensation going on, so you have latent heating and so forth. There's lots of things going on every time step. So, and this error here, the individual contributions to these terms that are being added up every time step come from different terms here, okay? So if we break this up, in our case we run at ECMWF a global spectral model. So what we do is we calculate the derivatives of the resolved motion in spectral space in wave numbers. So which becomes larger, of course, with resolution as well, because you have more wave numbers. And then we do spectral transforms into grid point space. We do advection, moving things around, moving water vapor or clouds from A to B. We apply our physics, convection, clouds, radiation, things like this. We couple with waves, then we have a solver, and we transform back into spectral space. And that's what we do every time step. So these problems have very different issues with computing. Our transforms are global transforms, so they're very large. So we involve global communication actually in this. So communication bandwidth is an issue, memory is actually an issue. Advection is done over an area, but you need halo communication for it because you move stuff from outside a certain box you calculate advection for into the box. Scalability is an issue of that as well. Physics are called single column, usually, so this is independent, so you can domain decompose them, so they're scalable, but usually they're very expensive. Simply the radiation scheme in our configuration is 15% of the total model, and we only use every third grid point and only run it once an hour because it's so expensive. So some of these are really, really expensive. The wave model as well, particularly with increasing resolution. The solver iterates, so that's expensive. There's memory and communication involved as well, and then same story again for the transforms back into spectral space. So I hope that illustrates a bit that there's quite a diverse number or range of challenges that we have to deal with in our model, and we have to deal with them somehow individually to improve on the individual aspects before we can, assemble the model and improve on the entire thing. And the number one though is that everything is sequential. So there's no way for a complex system like this, with so many degrees of freedom and such a nonlinear system, to actually do that parallel in time. So the more time steps you use, the worse it gets. So in our case, 10 days times 24 hours, so that's a 10-day forecast. Time step is about this. We have like 2,000 time steps. So the bigger you can choose your time step, still having accuracy and stability, the better it is. So this slide, many of you have probably seen. It comes from Thomas Schultes. He's shown this graph, for example, at the last year's HPC workshop at ECMWF. And it just shows you how important it is to work on everything together. At the time, MeteoSwiss in this case, so the Swiss Weather Service, was faced with the challenge to improve the grid resolution. So we spoke about that, ensemble prediction, and adding data simulation, so the initial conditions on top, which created a certain growth with the same budget. So they had to pull back that cost curve to where they could afford actually running these things. And there were a number of factors that they tried, but eventually the biggest investment they had to make was in software development. There was some that naturally came from being able to buy more processors for the money, or Moore's Law, but eventually the biggest investment needed to be made in software. And the largest factor in terms of staff investment was actually developing a dynamical core in CUDA from scratch. And that was many, many, many years to do. Okay? And of course this came with a bonus in reduction in power. So this is kind of the effort you have to make to gain back factors of that kind of magnitude. Now, I mentioned the ESCAPE project before. What we do there is something similar. We start with our global model, and coming back to the sequence along the time step I've shown, we try to extract the individual parts, like the physics, like the advection scheme, like the transforms, and then we try to deal with these problems individually before we put back the model together. So we call them dwarfs because they have some similarity to similar type dwarfs, more in mathematical terms or solar terms, that have been derived elsewhere. So these are weather and climate dwarfs, if you want. We adapt them to certain hardware types that we have available in the project. So Intel, that is an optical processor, quite interesting actually, and GPUs. That involves, of course, investment in programming models of this type or another. And then we look at exploring alternative numerical algorithms that may actually be better suited for one or the other hardware. And eventually we want to reassemble the model. Right, a result, this was provided by our colleagues from NVIDIA. So what you get, for example, if you take a smaller size problem, this is a spectral transform. So this was the first dwarf at the top of the time series. Spherical harmonics, spectral transform, this is about, TL159 is about a 128 kilometer resolution, so like climate model type resolution. This can be run on a single node, it's not too large. And we started with this kind of performance in terms of arithmetic density and performance in flops. And then you see it took quite a number of improvements in different areas. You know, the way you batch your matrices that you deal with, the way you manage your memory, but eventually we could achieve quite a good performance improvement, both in terms of data intensity and eventual flows. Okay, so that's very good. That's one of the things we do in Escape, and ideally we do this for all these dwarfs and all the hardwares. So multiply this by dwarfs and by hardware. And then if you go to higher resolution problems, this is a higher resolution here, corresponds to something we do in ensemble prediction these days, 18 kilometers. Then you play with this across nodes, GPU nodes that is, and I like very much this display here because eventually, I mentioned before, we are a time-critical application, so we need to fit our forecasts into 1 hour. So time spent on this per time step, times 2000, I mentioned that, is important, and energy per time step is important as well. So here you see, for example, if you scale from 8 to 16, there's hardly any price to pay in terms of energy, but you halve your execution times. That's great. If you go further, you see eventually you become very inefficient and you use a lot of energy and the GPUs basically don't do anything. Really, the problem is then too small for it. But you can trade off energy and time to solution doing this. And again, we want to do this for all the dwarfs in the project. A very important concept, and that is a heritage from what I've shown about CSCS. The Swiss approach is to invest in DSLs. So structures and programming models that take away and separate the hardware-dependent part of the code from the actual science code. And we invest in this in two different ends. One is what we call the Atlas library that allows you to represent all kinds of grids and meshes on a sphere. Allows you to do domain decomposition, and that allows you implementing a variety of discretization forms and solutions and formulations of your equations, depending on what you want to do. And this builds in a certain scientific flexibility. That's very important because depending on the choices you want to make now or in 10 years, you want to have some flexibility and not fix yourself too much to one solution that you may regret in the future. And then it allows you dealing with all the fields that are required and that you need to address in these solutions on the sphere forever. And that's then linked to the GridTools library, which is the Swiss development, which is a highly optimized kernel library that interfaces with Atlas in this case, and that allows you to perform all kinds of operations on different types of grids, and on the back end, different types of architectures. And the idea, in the end, is to separate that part from the science part so that the scientist doesn't have to deal with it. So we think actually that in terms of weather and climate applications, an investment in DSLs is maybe the only way to be fast enough to catch up with the HPC development fast enough to be efficient and portable at the same time. So there are all kinds of directions of research right now at the interface between weather and climate and computing that we currently perform. I mentioned already the investment in DSLs, for example, numerical algorithms, different options. I mentioned the scientific flexibility that we require and so forth. But there's lots more. There's precision. I showed you the scaling graphs were precision. We're looking very hard into precision because that's a very easy to get performance gain. We're looking into hardware faults, so resilient systems. And that always has, of course, a sidetrack and link to potential hardware, that single precision hardware or faulty hardware that can come with efficiency gains on its own or energy gains on its own. The Atlas library I mentioned, programming models, very important. I mentioned DSL, but we're looking at other things as well. So there's a whole area of new research projects being started just in the vicinity of weather and climate, just to make it more computable. And that's very interesting right now. So about a year ago, I had a talk with Peter Messmer from NVIDIA, I think it was over a beer, and he said, like, you know, can't you do weather forecasting with neural networks? I thought, like, no way. There's no way. And then he directed me to publications like this, you know, where big companies invest a lot in this area and produce weather forecasts commercially available. Some of them have their own observations that they use to have an advantage over others, over competitors and these things, you know, and they all invest in deep learning and so forth. So when we looked at that, or when we thought about this, there's basically 3 levels of question you have to ask yourself in that context. So actually, the top level question would be, can you actually really replace the full dynamical model that I explained, with the resolution, the equations and all that? Costly, of course. Can you replace that with a neural network concept or deep learning concept? Then you could go 1 level down and say, well, if that doesn't work, then maybe you can replace certain model components, which are very costly. I mentioned radiation, for example. I'm going to come back to that. And then lastly, and I think this is mostly actually the area where these companies are shooting, is really the short-range forecast that is based on data analytics, that is short-range, let's say a day or 2 forecasts, that involves a lot of post-processing and bringing together observations and model data from various sources, that tailors it to a specific user and location, for example, and need, and then also attaches to it some impact modeling. So what does your weather forecast actually have an impact on energy, or something like that? So this is, I think, the biggest business model. So question 1 again, weather forecasting per se. So what we did is we came back to Ed Lawrence, and he has published in the context of this foundation of the chaos theory, simplified models that are very nice. And he demonstrated the very nonlinear behavior and the strong dependence of your forecast on initial conditions using these models at the time. And then introduced this concept of how important it is to have accurate initial conditions for a highly nonlinear problem, and how chaotic the system can respond if you don't know that. Okay? So we used one of these models. It is chaotic, it's very nonlinear, you can play with that. And it really represents, in a very simplified way, what's happening in the real atmosphere. And the model looks like this. It has like 3 layers, X, Y, and Z, and you have a number of parameters in each layer. These are the large-scale parameters, these are the medium-scale parameters, and these are the small-scale parameters. So this would be like large-scale synoptic weather patterns. This would be like embedded waves, let's say, and the small-scale ones would be something like convection. So they correspond to different scales. And the model is really just these 3 equations, and they interact with each other, obviously. Okay? So limited number of degrees of freedom. So we use that model to set up to test the idea of, well, can we replace it or not? And I have to admit, we're not experts in neural networks, so we took something off the shelf, played with it, so it's not the end of the story, of course. So what we did was, we run that model for all the 3 parameters, 3 equations, 3 prognostic parameters. That's our truth. So we do a perfect model experiment because we know the truth. That's very convenient. So then we run a weather kind of model where we basically just use this equation and we neglect all the small scales, and that causes an error. And that's basically what we do in weather prediction. We have no perfect resolution, so we neglect certain scales. So this causes an error, and that's what makes weather prediction inaccurate. Okay, so that's a good approximation. 3, we train the neural network with the truth, and this is some data that we tried. So for training it, and then we try to predict X, just like the real model, with known initial conditions, and that's our neural network. And then we compare both with the truth. Okay, so little academic exercise. So what you see here, this is forecast time, this is forecast error, and this is against the truth, so the true model. This curve shows you the low resolution model, so this would be equivalent to your numerical weather prediction model. And then you have 2 colored curves that relate to the high resolution neural network, so where you know the starting point, the initial conditions for X and Y, so 2 different scales, and you try to predict X for different ranges. And the difference between blue and red is that you use less training data. So this is 1 million samples, this is 10 million samples. And it's interesting because I think it shows you actually a reflection of truth, that for the short range, as long as you have enough training data, the neural network is actually not bad. Even though it's such a simple way of doing it. But with forecast range, it deviates. And then, of course, the strong impact of having less training data or more training data. So it's just a demo, and as I said, we're not experts in neural network, but I find this quite interesting, and we're going to pursue it because we want to continue research in this area. So example number 2 is replacing forecast model components. I mentioned radiation as being one of the very critical and important costly things that we do. I mentioned this number already, 15% of the total model cost but even at reduced resolution and not every time step. So very costly part. So it would be a great candidate for replacing this with neural networks. And there's actually some history. We've done actually this. This is a guy who worked for us some time ago. We invested in this. And what he did at the time was he needed one network for each layer. So today, 137 layers, so times 2 for each direction. And he really needed a large number of input variables for temperature, pressure, and so forth. So it was quite a pain to train that. And in the end, he produced forecasts, and you cannot distinguish these two curves just a little near the end of the 10 days or something, but for the first 5 days, that's actually quite good. They're quite close to each other. So the curves and the symbols, so neural flux is the neural network replacing the radiation scheme versus the real forecast. That's quite good actually. But it needs to be trained on a large number of profiles to get that performance. It needs to be retrained every time you change the model, and we do this twice a year. But it achieves about 8 times faster performance at the time. So here's real potential, and therefore I think we need to continue looking at this as well. So lastly, the data analytics, and I said before, this is I think what most of the business model is about in this case. So it's mostly very short-range forecast. It focuses on a few key parameters like temperature and precipitation, but not necessarily the full 3D state. So it's very localized, and then a few parameters. I mentioned as well the observations and model-based, so the access to a certain information that nobody else has in terms of observations. So model helps, of course, having a better product. It's usually downscaled for local forecasts and the downstream implications I mentioned as well. So I think that's the real thing, I think, for this type of application. But I mentioned before the other two I think we need to investigate. I need to say 1 or 2 words about data. I referred to computing so far only, so that's very important. This is our production chain between data acquisition, observational data, running the forecast, generating products, and disseminating the thing. And just like the forecast, all this is on the clock, so you need to get the data out as fast as you can. And the factors here are the growth factors of each of the data volumes for each of these steps that we expect in the next 10 years or something. And some of these numbers are really frightening. Okay? So in parallel to the science challenge that I mentioned, so the 1 kilometer global at a rate of a year per day or something, we have a data challenge, which is to post-process that kind of data. And ideally, you do this in real time. So as you go with your model and you calculate your time steps, you run the post-processing at the same speed, so you don't have to do it sequentially after. And imagine doing this, that would save us about half an hour in our daily routine, and you could invest that half an hour in a more complicated model, for the same time. So that's a very important investment. Right. One aspect of this, of data, is that in terms of benchmarking, what we do is mostly, or has been in the past, mostly focused on computing. So we issue a forecast model or different incarnations of that, and then we give it to vendors and they run it, and who's faster wins, this kind of thing. But there's never data handling or I/O involved, and so it's very difficult to convince vendors to embark on data handling, benchmarking, of course, and competitions, but it's also very hard for us to do that, actually. So we have one new development that actually Thiago over there is leading in the context of the Next Gen I/O project, which is another project funded by the European Commission, in which we actually try to simulate the I/O workload that happens in our system. So it's very easily portable because it's a simulator. It runs dummy routines, if you wish, that produce the same profile of reads and writes in terms of access of disks, in terms of MPI communication, for example, in terms of data volumes as the real thing. And that makes it easily scalable and easily portable to other applications. So this is called Kronos. And if you talk to Thiago, or if you have time in the course of the week, please ask him questions about this. But very important new development. It's going to be very important for us for future procurements. So I'm coming to the end. 2 more minutes if I can. This is a graph that we published some time ago, and it's based on another graph that you've seen before. It puts again back into one graph the challenges along model resolution as you go from coarser scales to finer scales, and model complexity as you go from simple models to more complex models. So this coupling axis and the resolution axis that you saw in the other graph before. And you have certain processes that mostly are located at smaller scales versus very large scales and phenomena. So these are seconds, these are years, okay, and global, of course. And then these blocks here identify challenges. You know, in these areas you have parameterization challenges. Again, these red terms: coupling, atmosphere to ocean, observation assimilation, so getting the good initial conditions. But computing sits over here and is right where we want to go. We want to go to more complex model and finer resolution models, and this is where computing hits us the most. And this is why computing and data handling is probably the #1 challenge for us in the next 10 years. And this is why weather and climate prediction is a very good candidate to trial for exascale computing. So, if we can get this animation going. I don't have a cursor here. If you hover over the graph, there should be, yeah, there you go. That's it. So this is from a 2.5 kilometer model simulation that was performed at Max Planck over the tropical Atlantic, and you see an incredible resolution that we're not able to resolve in our models. I mentioned 10 kilometers, kind of the ballpark we can do today. But if you see this kind of detail, this is where we want to go. And this is only halfway to where we want to be, because we would like to do this globally at 1 kilometer, fully coupled and fast enough. And that's the challenge. So at ECMWF, this was mentioned by Thomas introducing me, we've launched a scalability program in which we try to look at these things, so data simulation, observations, the model, deep learning, these kind of things. And this is kind of a matrix along 3 different directions: our member states, industry, and academia HPC centers we're actually collaborating with, and the list is growing. So it's a very important project for us, but certainly larger than ECMWF, and probably larger than Europe even. It's a global challenge and a global partnership. And this is why it's a good thing to discuss that at ISC or SC for that matter. So, and the question then is actually the context that we have in terms of funding, ECMWF or some projects supported by the European Commission enough? Or is that not actually something that should be a flagship? It is a game changer. It is true that game-changing prediction capability has enormous societal relevance in our case. It's good for Europe because it adds technology and impact leadership in a science area where Europe is already a world leader, so very interesting. And you should look wider than weather and climate, because there's a value chain from weather to climate to energy to food and water. So this is a flagship level challenge, and across science, technology, and services. So this entire weather and climate challenge that we have, where we need to go, and we have formulated our science challenge quite well, requires probably an investment of that kind, and maybe not just European, but internationally. And with this, I would like to thank you for your attention.